Now we are ready to learn some important rules based on those test theory that we have covered. The first one is commutative laws. Okay, so A union B is the same as B union A, and then A intersection B is the same as B intersection A. And I would just say quickly here, you can really quickly prove this using our Venn diagram. Okay, A union B, B union A, right, is the same as what we're talking about over here. And let me use a different color. The intersection of the two, as we know, is the shaded area, the blue shaded area here. So it's commutative because whichever order that you're going with will give you the same results. Okay. Associative law is also pretty similar in some sense, right? Now we're adding adding a third event over here. So if I'm able to draw my large box, and then we do what? A, B, C, okay? A, B, C, okay? So the first one, again, is about the union of them, right? So we know that the union of the three will be all of this shaded area in red, okay? And as you know, you can union whichever order, and you can even do, I guess, A union C first, and then union B. And then similarly, when we're working with the intersection, well, in this case, it's actually only the small little area. Let me actually just like shade it all together so it's easier to see in blue. Okay, so again, it's only one piece of space that we're talking about, the intersection of the three. And then which order you're going, it doesn't really matter. And that's what the associative law is telling us. The third one is slightly less intuitive, but very interesting as well. Distributive law, okay? So if you read it, this is saying that A union B, the union of it, if I take the intersection with C, it's gonna be the same as I take intersection of A and C first, also take intersection of B and C next, and then I take the union of the two. So, as what we have done before, we can use the Venn diagram to efficiently prove it. Okay, so let's do A, B, C one more time over here. Okay. A, B, C. Okay. All right, so A union B, let's see. Let's do this slowly. A union B and the intersection with C. So we know that it will be all of this area. I'm not shading it because I don't want to do the eraser later, but bear with me here. The darkened, thickened, I should say, this area, but then we're doing what? Intersection with C. So it's gonna be only this one. Okay, this is the left-hand side if I do that way, okay? If I'm doing the right-hand side, let me use a different color here. I need to get A intersection with C first, right? So that's here, okay? And then also B intersection with C, right? And then I take the union of the two, okay? So again, for the left-hand side, I use red for this graph, okay? And then for the right-hand side, I was using the blue in my reasoning. And make sure that you know how to do either one and then show that they do match, okay? And I will leave the last one for you. To read it really is that if you want to get the intersection of A and B and then take the union of C, you can do it as taking the union of the two unions first and then take the intersection. And lastly, a rule is called the De Morgan's law that could be very useful as well. And to read it, as you can see, A union B and then take the complement of that is actually equivalent to the complement of A and complement of B, and then I take the intersection. Okay, and as we have done before, okay, let me use our good friend Venn diagram to show you this. So you can have S over here, okay, A and B. Okay. All right, so I'm gonna use a red to represent the left-hand side. A union B and take the complement, right? So A union B we know is all this area, but we're taking the complement. So it's going to be everything outside of it. the left-hand side, sorry, right-hand side, let me use blue. So A intersection, sorry, A complement. So it's going to be everything outside of A. Okay, let me use this color. Outside, okay. And then also everything outside of B. Once I do the outside and then take the intersection, you can see that it's exactly the same as what we're having over here. Okay, and similarly, you can do, you can show why the second one is true, that if I take the intersection, take the complement, okay, it will be the same as taking the complement first and then take their union. Okay. You can also do this more mathematically, okay, left to right and right to left. Okay, think about a particular element. You can also, again, draw your Venn diagram and think about a specific element like X. Then you're able to show, again, how De Morgan's law apply. Okay? And lastly, let me just show you that the De Morgan's law can be generalized to n events. Okay, so remember, we only had two to start with, A and B, but the result is really generalizable to n different events, A1 to AN. Okay? And what that tells us is that if I first get the union of all of them and then take the complement, that's equivalent to take the complement first and take all of the intersection. Similarly, if I take the intersection of all of them first and take the complement, that is equivalent to take the complement first and take their union. Okay, so make sure that, well, this applies in a higher dimension, meaning that more than two events. That makes sense to you. And to quickly recap, I include a link actually here to understand De Morgan's law proof a little bit more. It's a YouTube link. And to recap of what we have talked about in these two videos, we define sample space and then a subset of it as event. The set operations or set theory that we have introduced, intersection, union, complement, subset, as well as mutually exclusive events and disjoint events, they're the same. Okay, the three rules, or I should say four rules in total, okay, commutative, associative, distributive, and De Morgan's law. And lastly, always remember that if you're a little bit unsure about whether things are working the way that you understand it, you can always use the Venn diagram. It is really helpful as you can sketch out a rough plan and then look at how the different events are interacting with each other.